Welcome back to the last session. So the idea now is to have two short presentations on available packages for very common and very used softwares like Stata and R. So these are packages that have been designed in order to make the analysis of data, assessment data from large-scale assessment easier. So they're nice because they allow you to take into consideration the specificities of the assessment data. So we have first a presentation from by Daniel Caro, who is the author of this package on R. Daniel.
Okay, I'm going to talk briefly about the R package INSPE. This is a package in the R statistical environment to conduct analysis with international assessment data. So it has three main functionalities. One is to merge and import data. Another is to analyze data, so to conduct secondary analysis, such as producing simple statistics like means, percentages, and regression coefficients with their associated standard errors that take into account the sampling error and imputation error that have been discussed previously. And it also has functions for visualizing the results. It handles different data sets such as PIAAC, PISA, TIMSS, PEARLS, and it's also extendable to other data sets. So I'm going to present examples here with PISA. First, just to refer to some online resources for learning how to use this package. So if you were interested in using this R package, you could, for example, have a look at some video tutorials and a PDF tutorial, as well as data analysis examples and some blogs that are part of this link. So if you go to this website, you're going to find some of these resources. There are video tutorials that will take you step by step from installing the package all the way to conducting regression analysis. There is an article that has been published in the Journal of Statistical Software last year that can be used as well as a tutorial for the package. It more or less explains the architecture of the R package, also the methods underlying the different functions, and it provides examples of how to use the package for PISA and other data sets. You also have data analysis examples on the website. For example, this is for PISA 2015, and it shows you from installing and opening the packages to importing the data and to calculating the most basic results. And you could check that those are the same as the ones that are reported in the international PISA report. And as I said, there's also some articles in R bloggers. As usual with these packages, so there is a stable version that is uploaded to CRAN, the comprehensive archive for the R packages, and there is also a development version. As I said, I'm just going to show you a few examples for basic analysis with PISA 2015. So we usually want to start with reading the data, so importing the data into the R environment. And I said that this package has three main functions. One is importing data, another is analyzing data, and the other is visualizing results. Actually, the functions for data importation and merging are much more relevant for other data sets, such as TIMSS and PEARLS, because they are structured in many different files by instrument and country. PISA You usually have two files, schools and students, so you can easily do that manually, so you don't need really to use this kind of function, but still, I will just explain how it works. So this is the function, which is PISA select merge, and it has different arguments, such as the folder where the data is located, the name of the student file, the name of the school file, the name of the variables from the student questionnaire that you are interested in importing into R, the name of the variables in the school questionnaire that you would like to import, and you could also include the countries, selected countries. So as a result of this function, where the user is supposed to supply all these arguments, you will obtain a data frame, which is here PISA, which will contain selected data for these variables and these countries. And the same logic applies to other international assessment studies. So now we have this data frame, and we can start conducting analysis with that data frame in the R software. So the most basic one, let's say that we are interested in calculating average performance, science performance. This is PISA 2015. So there is a function that is called PISA 2015 mean.pv, and the user needs here to enter some arguments, such as the data set. If I want to conduct the analysis by country, then I could enter here the label for the country variable, and I enter here also the label for the plausible values. And as a result, I'm going to get the mean, it's a standard error, the standard deviation, and the standard error as well. I can also export this directly. I mean, here is only a few countries, but I could have all of the countries. And I could also have more groups. So I have considered only the country, but I could have more grouping indicators, as we will see in the next example. But you can export, so there is an argument to export, which is set to false, but I change it to true. And as a result, I will obtain a spreadsheet that I can directly import in Excel. I mentioned before that you can have more than one group. So now here we have country and the student sex. So now we have two results for each country, right? For each country, we have the mean for boys and girls, and the standard error, and standard deviation, and standard error too. Another functionality that I mentioned is visualizing results. So here I can store the results of this function, which is science performance by country and by student sex. I can store it on an object that I'm calling science sex, and I can plot it. And because the plots in the R package IMSB are based on another package that is called ggplot, you can also use ggplot language to customize these graphs. So I'm here adding labels such as girls and boys for this plot using ggplot language. Now, that was an example of average with plausible values, but you can also calculate averages without plausible values. And then you will, again, have a function that is called PISA 2015.mean, but now it's not PV, it's just mean, right? So usually the functions in the package will differ in that sometimes you will have this ending PV or not, depending on whether the function is applied to variables with plausible values or not. So here it's not. Thank you. So I'm just calculating here the mean of the SES variable. This is the socioeconomic indicator in PISA by country. And again, I get the mean, the standard error, the standard deviation, and the standard error by country. Can calculate frequency tables as well with the package. So let's say I'm interested in knowing the percentage of students by school grade in each country. So I can use this function, which is PISA 2015.table. And there is an argument that is variable, and I will enter the variable that I would like to tabulate. And in this case, it's the school grade. And I do this by country. And I will get, and as I said, this here only contains one grouping variable, but I could include more than one group. So here I will get the percentage of students in 7th, 8th, 9th, 10th grade, and it's a standard error as well. Proficiency levels, so we have them in the different assessments. So we can use, for example, here, PISA 2015.ben.pv to calculate students by proficiency level. And because those levels take cutoff points that vary depending on the subject, so I will enter those manually here. So there is an argument that is called cutoff, and I will enter the cutoff points here, and it will give me the percentage of students at each level. Regression analysis, you can also conduct regression analysis with INSBE. So as before, as I said, there are functions that will have this will end with PV and others that will not. This would be, for example, regression analysis where the dependent variable is science performance, and we are indicating that with this argument, PV label equal to science. And our independent variable are here the student socioeconomic status and also the school grade. We are going to conduct regression analysis by country with this data set. And we will get coefficients, standard errors, and t-values. We can plot as well. So if I want to store these results from the previous regression on an object, I can plot the regression coefficients. This is not very nice, but I can also change this. Here I have the intercept, I have the coefficient for the school grade, the coefficient for SES, the R-square, but I can also select a specific variable. So if I say just plot this object, but for these two coefficients, I can just plot these two coefficients, the coefficient for school grade and for SES for these countries. And yeah, it's always the same logic. So now if I wanted to conduct regression analysis without plausible values, so for example here for sense of belonging to school, I would use PISA 2015.rec instead of .rec.pv. And again, I will indicate independent variables with X, and the same arguments apply as before. So I can calculate here the association between SES and sense of belonging in school using a regression approach by country. Thank you. So yeah, that's it. Thank you very much.
Thank you, Daniel. And now François Keslair, who works at the OECD, will tell us about a similar package about, on the Stata platform.
Hello. Sabrina, can you launch the slide, please? So is Francesco still here? Okay, that's cool. It's free. All right. So I'm going to introduce you to Repest. I was asking whether Francesco was here because he's the co-author of Repest. He started working on it, and then I joined him, and we finished the project together. Okay, just to come back to what has been said before in this seminar, we talked the whole morning about measurement error. We had some few about sampling error today, this afternoon. What's kind of funny is that we call some statistician called measurement error also non-sampling error. Just to give you an idea of how important sampling error is, there are many different measurement errors we can think about. We only talk about a few of them this morning. Same thing about sampling error. I'm not giving you any list of them because that's kind of crazy. And afterwards, you're a bit scared of every error that could exist. So this type of error, they can impact point estimates. And that's what we talked about this morning, meaning what kind of bias can cause the latent variable model, the population model, and so on when we use them in secondary analysis. What we did not really talk about this morning was the impact on standard errors. Sabine talked about it a bit this afternoon, and we're gonna have a say about that, and the use of repest. It's not about eliminating bias in point estimate. It's about computing correct standard errors that account for the sampling error and the measurement error due to the imputation of plausible variables. Okay, so repest, I should have said that earlier, but that's a Stata routine, and as Daniel presented a routine about R, repest is some kind of equivalent for Stata. It's been published on IDS Repeg, so you can download it easily. And so it's designed for complex survey design, meaning taking into account standard sampling errors properly, and also in the same time taking into account imputation error with plausible values. So we wanted to have some generic tool that would be used by everyone at the OECD working on the international large-scale assessment, and I mean PISA, TALIS, PIAAC, and it's also working for TIMSS and PEARLS. And because before that, you had a different routine for every survey. That was kind of annoying. So we have something universal, and the reason why it's universal is because the method is universal. The way we compute this sampling error and imputation error, it's very simple in a sense. We compute an empirical distribution of all statistics, and then we applied a formula that's going to compute from this empirical distribution the standard error, the impact of sampling error and of imputation error on standard errors. So that's the empirical distribution I was talking about. So the first column, it's about the sampling error. The way we compute sampling error, we use balanced replicated weights, and that's again all across the OECD education survey. We have balanced replicated weights, and each of them is more or less an alternative sample. And once you compute your statistics of interest across all these weights, then you manage to have an empirical distribution, and from this empirical distribution, you're going to have a standard error. That's the same thing with plausible values. We have different random draw of plausible values, and that's it. And here's the formula we apply. It seems to be complicated. The thing is, it's not that just empirical variance, empirical variance for the sampling variance, empirical variance for the imputation variance. So the syntax works this way. Just look at this part. So that's more or less very close from a Stata command. And repest is going to work as a shell. You need to specify the survey name, the Stata command inside estimate, and then you can also specify that you want a result for every country. And this simple line, it's going to give you correct standard error for this table. And it's another example. Right here, we have a plausible value. That's the score for science in PISA. You just replace the number for plausible value by add symbol, and that's fine. and we want result for migrants and non-migrants. We add this specification, and then we're going to have a population estimate for migrants and non-migrants, and even test the difference very easily. So that's a next step from the L5. The cool thing is I'm not the one who wrote the L5, so it's very well documented, it's very well written, and that's more or less the only thing you need in order to understand how requests work. So it's perfectly comprehensive. So to conclude, what request can do, it works with any E-class command, which is a cool thing. You don't have a specific command for mean, specific command for regression, and so on. You can adapt it to any large-scale assessment just by changing the name of the parameter, and we can also export results differently, either on in the store function from Stata, or as a DTA file. Okay, thanks for your attention. I'm done.